something running from 0 to infinity. Taylor series. But that, do we not need some spot to do Taylor series on? Don't we need some x0 where we do Taylor series? Really small angle, second order approximation. No, linear is way better. Harmonic oscillator. Yes. Good morning, fellow mathematicians. I have to admit, I look pretty good in this shirt. I just love this thing. It's from G-Star Raw. It's just the best brand ever, okay? I really do enjoy G-Star Raw, okay? Daddy loves it raw. After this awesome, totally mathematical introduction, we are going to take a look at something kind of exotic today. So, if you've ever done quantum stuff, it's not too much of an exotic thing. It's just kind of standard, but most people never saw this before, have never seen it before, and that's why we are going to take a look at the shift or evolution operator, or how other people like to call it, the exponential derivative, okay? But that's not how we are going to call it, okay? What's the shift or evolution operator? For this, I would just like to take a look at something really simple, okay? Just some shifted functions, shift operator, evolution operator. So we are going to take a look at the shift in the function. For example, the sine function shifted pi over 2 to the left or right, okay? Let us just take a look at some function f, which is, I was using the wrong side of the Hagoromo-Checker, I'm terribly sorry, f of x plus a, where a is just a real number, okay? Let's stick with real numbers right here. You can also do it complex, but it's going to result in something that has really no applications at all. Not yet. Not yet, my boys and girls. Now, we want f to be a function from R to R, okay? Let's just clarify this for a second. And one more important thing is we want f to be analytical, meaning in layman's terms that you can turn it into a Taylor series, okay? So we want f to be element of c omega from some interval, okay? This is just how you would denote it. For example, from negative infinity to infinity. I really don't care from a to b, but I'm not going to use a right here because we are using a right here at the moment. Now that we got this out of the way, I would like to turn this into a formal Taylor series expansion. That's why I wanted it to be out of the space of analytical functions, c omega. Meaning, this thing as a Taylor series does nothing but something running from 0 to infinity. Taylor series. But that, do we not need some spot to do Taylor series on? Don't we need some x0 where we do Taylor series? Really small angle, second order approximation. No, linear is way better. Harmonic oscillator. Yes, my sons and daughters, we do need this. And we want to do something that probably goes against many people's beliefs. We are going to do a Taylor series expansion in x right here. Meaning, if we take a look at a more formal Taylor series expansion, it's going to result in the kth derivative, in this case, at the point we are going to do the Taylor series in x over k factorial times, okay, this argument, x plus a, minus the point we are going to do the Taylor series in, to the kth power. Meaning, if you take a closer look, this and that is going to cancel out. We are going to be left with a to the kth power. Also, what is the kth derivative exactly? Well, this is the derivative of the blah 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 up until the kth derivative in our f. I'm going to denote it using the d, okay? Everyone loves the d, I do love the d. We are going to use the d because we love it. This right here, k being equal to 0 to infinity of the kth derivative of f in x over k factorial times a to the kth power. Now, if you take a closer look, if we bring this f to the back right here, okay? We can't bring it to the front because our real operator is acting on it. What exactly is this thing right here? Okay, we can collect a and d, both to the kth power, and this thing right here is just our exponential function, just with a d plugged into here, okay? E to the a times d of f. of x. This right here is our shift or evolution operator, and it comes in many different forms, variants. Okay, in quantum mechanics, for example, you are going to encounter this thing all the time, because what you can do, instead of a d up here, you can plug in a momentum operator, for example, or yeah, I don't know, maybe probably also a Hamiltonian or a Green's operator. I really don't know. Many things you can do with this, but this thing has a lot of applications. And this is our shift evolution operator. It's the exponential derivative. And do you know what's really cool about this thing? Well, in the normal case, if you do derivatives, you can encounter many problems. Doing the derivative of the absolute value, it's going to be a mess in zero. It's not differentiable there. But here, well, it just converges overall to shift in this function, and this is really good. This is what many people use it for. And more formally, there are many kinds, okay, of those translation, evolution, shift operators. They overall form a group under composition. It depends on the kind of composition. They even form a Lie group. So this thing right here is infinitely often differentiable. It's a smooth function, our f, meaning it forms a Lie group overall. Okay, and in the normal case, more formally, we would like to denote our operator right here as this tau with the shift of f. Okay, this is just the translation tau, t translation. I hope you can see where this notation comes from. Meaning, if we take a look at a certain set, okay, this is the set of all the translations, we are going to define it as follows. This is just, like I said, the set of all translations with unit a right here. We are going to shift it a units to the right or left, whatsoever. And this thing is actually nothing but, let me see, we are going to take a function out of our, so we are going to plug a function into here. That's an operator, meaning we have to go from a function space to function space. It's going to spit out a function from some interval, c omega of some interval, to, well, kind of the same thing, but with a shift in a right here. We are going to shift it, for example, a units to the right, meaning negative a, for example. Dot minus a, comma, dot minus a. Okay, really depends. And the only restriction on here is basically that we have a being element of R. If you would choose a to be element of c, that would just result in, well, the sine and cosine derivative. Like I said, it really doesn't have any application. But for this thing right here, it really has many applications. And one really cool thing, that's a really nice math nut right here for you, okay? You can actually define our standard derivative and the multivariable partial derivative using this translation right here. And this is something really cool. And in, for example, what is it? Scattering theory, quantum scattering theory, you are going to use this sometimes, often, a lot. Okay, so this is the first thing, and after we were talking about that, I would like to prove that this thing right here forms indeed a group under composition, and we are going to use our e to the ad for that. Okay, but at first, here comes the really cool part. That's the most exciting part for me of this video, okay, about this video. We are going to take a look at our del, okay? This is our partial or regular derivative, and we are going to define it as the translation inverse, okay? What this is, we are going to talk about in a minute when doing the group theory stuff right here, times the derivative of our translation in A. This is how we are going to define it. This is our partial or standard derivative. What is probably going to be the inverse of the translation? Spoilers ahead, it's going to be just tau of negative a when it comes to our exponential derivative, for example, okay? This is just how it works. When we are going to do the group theory stuff, I'm going to go into more detail about bijectivity and stuff like this, injectivity, whatsoever. Now we are going to take a look at the derivative of some function f of x, okay? Meaning, if we take a look at del f of x, well, in a normal case, what we would expect, it's a single variable function, it's just f prime of x, okay? ddx of f. But we are going to use our shift operator definition for that. Meaning, this is nothing but our tau inverse, so our inverse translation, times the derivative d tau a in a of f. Now we can simply start using definitions. We know that there's the difference quotient, so the standard limit definition of the derivative, meaning overall this is tau inverse translation. Then this is the limit as, for example, I don't know, epsilon approaches 0. Okay, epsilon never 0, Papa, how can you do this? Fuck off. Okay, epsilon's going to go to 0. I said it, we are going to do it. Limit as epsilon goes to 0 of tau of a plus epsilon minus tau of a over epsilon applied to f. Now, if you take a look at here, for example, on this translation operator, we can just bring this f to each and every part, okay? So here we would have, for example, e to the a plus epsilon times d minus e to the a times d, and then we can just distribute the f into each and every part. Meaning this is going to result in tau, inverse translation, limit as epsilon goes to 0 of, I'm going to do step by step, tau a plus epsilon, and then f applied to it, minus tau of a, and then f applied to it over epsilon. And here comes the really cool thing, because we know what this is going to variate to, and we know what this is going to variate to. It's just a simple shift. We have defined it before, okay? This is going to variate to just the shift that we have as the index right here. Meaning, this is tau of negative a, and I'm going to denote this limit now as capital L. And then we are going to have f of x plus a plus epsilon minus f of x plus a, I'm terribly sorry for the cramped space, over epsilon. And if we now choose this x plus a as our argument right here, okay, something that we have, then we are going to have f of u plus epsilon minus f of u over epsilon. And if we let epsilon approach 0, it's just a simple derivative in our f of u, which is f of x plus a, leaving us with tau of negative a, and then we are going to apply to it just a simple derivative right here. Okay, that's an ugly bracket. This is just what we have. This is just a derivative definition. And now we know how this works. If we apply a function to our translation, we are just going to plug everything in. F prime of x plus a minus a is thus nothing but f prime of x. And this is differentiation for the sophisticated gentleman. Okay, this is just absolutely wonderful. And with this technique, you can actually get rid of many problems in differentiation theory. You could say, okay, differentiation is a bit easier using this, even if you're dealing with ugly functions. And now we are going to go for, we are going to start off with the group theory stuff. Okay, give me a second. Top of the morning! Let's go ahead and get started. So, shift operator. This is our set of all the shifty boys, okay? And we want to show that our set right here under some composition being defined like this is going to form a group. It's also going to be an abelian group. Spoilers ahead, okay? This is something that works out, and I mean, you can immediately see why it does form a group, so you don't even need to check for everything, because it's absolutely trivial. But let us still talk about that. Does it make sense to you why this right here holds? Okay, why tau a in composition with tau b is going to result in tau of a plus b? Well, if you think about it, this right here is tau a of tau b of f, meaning this is going to be tau a of f of x plus b. Then we are going to apply our shift once again. So this is tau of x plus a plus b. This is tau of a plus b applied to our f. Okay, with that out of the way, it does make perfect sense. And it even does make sense for our e to the ad right here. Okay, this is basically our shift operator that we are going to use now. Okay, now. We're going to use it now. Meaning, let us first talk about this right here, if this even holds. Meaning, e to the a times d in composition with e to the b times d. What is this going to be, this composition? Well, it's just regular multiplication, okay? I hope it does make sense. And to be more formal, we have to apply a test function to it, because it really doesn't make any sense to use the differential operator on nothing. So to be more formal, that's what you would do in quantum mechanics, for example. If you want to find out something about the commutator group or the value of a commutator, we would have to use a test function on this whole thing, just because of differential, real operator right here. Now, we want to know if this statement right here is indeed true. Well, it is. Take a look into the description. I made a video why this function equation even holds in the real complex numbers, for example, and it even does hold for our operator right here. The only real restriction is that our a and b do indeed commute, because we are going to end up with the binomial theorem. Take a look at the video, it's really important right here. It's not obvious why this right here works if you were dealing with matrices up here, which do not commute, for example, as the operator. You would be fucked. This right here would not be true if our D, for example, would be a non-commuting matrix. So this right here is the first really important step, just because A and B does commute, and also D to the n minus k times d to the k, so applied to it is just d to the nth power, okay? That's why it does work out. Write everything out, take a look into the description. It's really important. This is not an obvious fact. You have to check. Function analysis and shit, you know? Now we can go ahead and check for the group properties. So the first thing we have to do is check for associativity, meaning overall that if we have 3 elements in there, we can change around our parentheses. Meaning what we want to check is if tau of A in composition with tau B in composition with tau C is exactly tau A in composition with tau B in composition with tau C. Okay, that's an ugly look. Tau, I'm terribly sorry. I'm going to go through it in an intuitive way, because we know that this right here holds. Meaning, if we compose all 3 together, we are going to get e to the a plus b plus c times d. But a and b are real numbers, or even complex numbers. Really doesn't quite matter, we declared them to be real numbers. And you know, the real numbers form a field. More implicitly, it's a group under addition already, meaning the associative law already holds for real numbers, meaning this fact right here follows trivially from the fact that our associativity is getting induced by our bigger structure R. With that out of the way, associativity has been a really marginal thing to do right here, okay, checking for it. Now we are going to check for the closure under the composition. Meaning, what we want to do for the next part, tau of A in composition with tau of B is once again element of our tau right here. Okay, for all tau A and tau B out of our tau originally. Well, if you write this in other terms, we are going to have e to the AD times e to the BD is thus nothing but this, e to the A plus B times D, but our real numbers already form a field, meaning it forms a group under addition. So this right here is element of R, like this. And well, meaning we have fulfilled our condition for our operator to be in our tau once again, in our translation set of translations. Coolio. Let us move on with the identity element. Meaning, we want to see if there does exist some I, for example, some Ti, so some real number I, such that we have tau I times tau A, not times, but in composition with it, is the same as tau A in composition with tau I, and this is the same as tau A yet again. Now we can write it out, and it's just kind of a formal thing to check for both sides, because for something to be an identity, we need it to be a left and a right identity. A right and a left identity. Okay, I did it the wrong way, but you were probably seeing it the right way. Okay, now we can take a look at our exponential derivative, you could say. Meaning, we are going to have e to the I plus A times D. Okay, I'm just applying this rule to this thing already. Okay, that's the equivalent statement used on some f. Okay, is thus equal to E to the A plus I D. And we want it to be equal to E to the AD. Well, for which values of I does this hold? Well, obviously, I being equal to 0, it's just a real number, it does hold. Meaning, our identity operator out of this tau right here is thus nothing but E to the 0 times D. I'm going to put it like this. And maybe you can see where this is going if we apply this identity to some function f of x. What is going to evaluate to? Well, f of x plus 0. So this is just going to be f of x yet again. It's the identity, like f of x being equal to x. It just maps the element to the same element yet again. It does make perfect sense if you think about it. It's really easy to check right here. Now for the last part. We want to see if there does exist an inverse element to each and every tau a, such that those two in composition result in tau of I. Meaning, more formally, tau to the negative 1 of a in composition with tau of a is thus tau of I. You have to check for the left and right inverse yet again, but we are not going to talk about this because, well, real numbers are abelian. We are dealing with real number arguments right here. And now you can do it in layman's terms and say, well, our inverse is obviously negative a because a minus a is going to result in 0 up here. And you are right with that assumption, okay? So if we just take a look at this thing right here, it's going to result in tau. I'm going to put it like this. That's the same as e to the a minus a times d, which is nothing but our identity in tau. This does indeed hold, but is it that trivial? Kind of, I think. I mean, it does make sense. We are dealing with real numbers, but to be more formal, you would basically have to check if there does exist the inverse of this operator, meaning we have to check for bijectivity. We are going to do this really quick, meaning we have to check if it's surjective and injective. 1 on 1 and on 2, okay? Now let us go for the injectivity. That's the easiest part. Meaning, what it does say, we have that tau a, I would say, let's put it like this, of f of x is equal to tau a of g of x does indeed imply that f is equal to g. Okay, this is what it must imply. This is what it means for something to be injective. Take a look at a graph and you're going to see what this is useful for, or take a look at Wikipedia. Well, if we just use the translation on those functions, that's equivalent to saying we have f of x plus a is the same as g of x plus a. And this statement right here does indeed imply f of x is equal to g of x. This is just what it implies. Just think about it, okay? Yeah, it's just what it is. So you can rewrite this argument as u, and then you are going to be at the same thing, okay? It does work out. Now for the surjectivity, and then we are basically done with this whole group theory stuff. Also, it's kind of obvious that this whole thing is abelian because real numbers are abelian when it comes to addition. So a plus b is the same as b plus a, okay? Abelian stuff out of the way, commutative stuff. So for the surjectivity, we have to check that for each, let's say g, out of our original space, so C omega, I'm just going to denote it as C, there does exist some f out of C such that, let me see, tau a of, for all, yes, f, this is equal to g. I hope I'm not mistaken on this one right here. Now, this is what it says, and now we can just apply stuff. So if this right here is g of x, meaning if we have tau a, f of x, this is going to result in f of x plus a. Okay, how can we get to some g of x? Well, our g of x must thus be equal to, or our f of x plus a must thus be equal to g of x plus a minus a. This is what we have to have right here. And we can certainly find such a function that this right here holds, such that this right here holds. And then we are done. This thing is bijective, meaning an inverse operator does indeed exist. I hope I didn't mix anything up right here. For G, we have some, yeah, this should work out. I hope you enjoyed this video. If you did, please like, subscribe, and recommend channel. If you want to support the channel a bit more, why does teachers I create also support channel on Patreon. No matter what you do, I thank you guys for watching. Up until the next video, have a flammable day. Ciao.